Okay, this is a pretty complicated problem. I admit to have seen it before, but let's go through the solution that I'm familiar with. We're told that we have a triangle where the cotangent of angle A plus the cotangent of angle B plus the cotangent of angle C equals radical 3. Prove that the triangle ABC must be equilateral, which in effect is the same as saying that angle A equals angle B equals angle C equals 60 degrees. And if all angles are 60 degrees, then the cotangent of those angles must also be equal. So in effect, we want to end up somehow with the fact that the cotangent of A equals the cotangent of B equals the cotangent of C. And then we can deduce from there that it must be an equilateral triangle. Okay, so that's where we're headed. Now, part one is to establish an identity that's used in the actual proof. And that we're going to refer to angle A, B, and C instead of the measure of angle A. I'm just going to use the letters A, B, and C to stand for the measures of the angles. So in any triangle, if you add two of the angles together, the third angle has to be 180 minus that angle. And if we take the cotangent of those equal angles, those cotangents will be equal. And this is a trig identity, the cotangent of the sum of two angles. And this is also a trig identity. And if we kind of simplify this, we multiply both sides by this denominator. We get to here, distribute the cotangent of C, and then get the cotangent terms on the left side and the one on the right side. And we're going to use this quote identity when we do the actual proof. And just to convince yourself that that identity is always true, here I am on Desmos where I labeled some angles A, B, and C, and I've typed in that identity, and you can see it's 1, and it doesn't matter what I do to these angles. That value is always equal to 1. And here's the cotangent of 180 minus C is always equal to the opposite of the cotangent of angle C. Okay, so let's go to board 2 and we'll talk through this ugly looking proof. This is the given information. What we're going to do is square both sides. And when we square both sides, getting from here to here, I've just made a note over here how you could do this. You could group the first two terms and treat this as the square of a binomial. So we'd square the first term plus twice the product of these two terms. That's cotangent C times the cotangent of A plus the cotangent of B, plus the second term squared is this guy out here. Okay, and then you could simplify this term by squaring that binomial and then group the terms accordingly. And this is what you end up with. But what I have done is when we move from here to here, I should say, we're replacing this expression right here from part 1 with the number 1, because that expression is always equal to 1. Subtract 3 from both sides, you get a minus 1 over here. And now here's the really tricky part. We have to multiply both sides by 2. And this minus 1, that becomes a 2, but then I kind of picture, it's hard to see, this is the number 1 here. Negative 2 is the same as negative 2 times 1. And what do I replace that 1 with? We're back to using that identity that we established in part 1 on tab 1. And now when we group the terms, I wrote 2 cotangent squared A as cotangent squared A plus cotangent squared A, and the same for these terms. So that I could use each of these in separate expressions. So cotangent squared A minus 2 cotangent A cotangent B plus cotangent squared B That gives me one group. And by grouping these terms, we end up with something like this. And each of those terms in parentheses, or those expressions in parentheses, are actually perfect square trinomials. So I can write that first one as cotangent A minus cotangent B, the quantity squared. Similarly, whoops, this should have been a C here. And cotangent B minus cotangent C squared. And now the idea is that if these terms separated by the plus signs are going to have a sum of 0, then each in turn must be equal to 0. Because no matter what's in here, if I square it, we're going to either get a positive number or 0. And the only way we're going to add 3 positive together to get 0 is if, in fact, they're all 0. So cotangent A minus cotangent B, the quantity squared, has to equal 0, but then if I take the square root of both sides, that's what I get. And then the cotangent of A must equal the cotangent of B. Similarly, we get the cotangent of B must equal the cotangent of C. And since we're dealing with angles of a triangle, these angles will have to all be equal. So angle A equals angle B equals angle C, and therefore equilateral. This problem is sometimes presented as an if and only if problem, which means if it's equilateral, then this statement is true also. Well, that's really easy to prove because each angle is 60. The cotangent of 60 added together 3 times will give you radical 3. So QED. We're done.